Wells are used for three main processes: to either recover some fluids from the ground, inject fluids into the ground, or monitor either the composition or the hydraulic head in the fluids. So for recovery, water is certainly the most common thing that we pull out of the ground, but also in the environmental industry, NAPL or non-aqueous phase liquids, air vapors, those are also important. And geothermal heat recovery is important for some applications. Environmental applications, either for remediation or for trying to limit the influx of contaminants into aquifers, involve injecting water in some cases, or possibly also injecting air. Here are some examples of some wells at the ground surface. This here is a water well in Mount Pleasant, South Carolina. This is a municipal well, quite a large production well. And over here, this is a well that's used for an environmental application called soil vapor extraction. That's what SVE stands for. And this has been constructed at the Lawrence Livermore National Lab. That's that acronym. And the well is there. Looks like there are a couple of wells here. There's one. There's one. There's one, and the wells are have plumbing to them that allow the vapors to be recovered and taken over to a processing plant. And this is an environmental monitoring well, so it doesn't have active recovery being done, so it doesn't have the surface piping that these other two examples do, but it allows us to go in and obtain a sample or measure the hydraulic head whenever that's needed. And here's a fairly simple water well being produced. So to create a well, there are several steps that we need to go through. This is a list of 5 steps that would be probably the complete set of steps. Not all of them are done in all cases, but the basic process involves most of these steps. There are variations on all of these steps, but this is the main scenario. So to create a well, you first of all have to drill a hole in the ground. Some cases you may sample the cuttings coming out, but maybe not, depends on what the needs are. And then once you have the hole in the ground, you have to what's called complete the well, and that changes the well from being just a hole to being something that would be durable and lasting and isn't going to collapse. The development process involves removing the fine grain material or some vestiges of the drilling process that are in the vicinity of the well, unclogging clogged pores, and allowing water to flow more readily to the well. And then in some cases we might install a pump. Okay, so step 1, we're going to have to drill a hole. We're going to have to make a hole in the ground. And there'll be a variety of ways of doing this depending upon the characteristics of the formation, but they have, by and large, these 3 different steps. We have to cut the formation. So we've got a solid formation in the subsurface, and we have to cut it and make so that we can get some of that material out of there. So we've got to cut it or disrupt it, and then the cuttings that we've created we have to remove. And then while we're doing that, we have to prevent this hole from collapsing. So the first step is to disrupt or cut the formation, and then we get those particles out of there, and so we've deepened the hole as a result. And we just keep doing that creates the hole, and then while that's going on, we have to prevent this hole from collapsing. So there are 3 main methods that are used in this area. Actually, 2 primary ones, I would say, in this area for creating wells. One is an auger, and another is the air hammer, and then the mud rotary in some cases. But these 2, the auger and the air hammer, are the most common methods of drilling wells in this area. So here are some pictures of auger drilling. In order to, and here are the things we have to do. We have to cut material, we have to remove the cuttings, and we have to stabilize the hole. So augers are used in relatively soft, unconsolidated material in sediments typically, or around here in saprolite. And the way that they cut is you can kind of get a hint on that right here. This is the cutting tip on an auger, and if you look closely, you see these cutting teeth that look kind of like that, and it moves like this as the bit is rotated. And so if this is the bottom of the hole, as this thing moves laterally, it cuts, and the material, the cuttings come up like that. Okay, so what's happening is right here at the bottom you have shear, and this bit is shearing along the bottom and cutting this material, and then ultimately it'll lift it up out of the hole. So the disruption process is happening in shear, and that works just fine so long as the particles are not really stuck together very well. And in sediment and saprolite, that's the case. So this cutting bit right here rotates, and you can see there are many of these teeth. So it rotates, that cuts the material, loosens it, disrupts it, what have you. And then to remove the cuttings, we see we've got this spiral, these metal pieces wrapped in a spiral, and that's the auger itself. So this looks very much like an auger that you might use in a wood shop, for example. And as this thing rotates, the particles that have been cut down here at the bit are conveyed upward. So that's how you get the cuttings out of the hole. And then to stabilize it, well, the way that this auger is set up, this is called a hollow stem auger. And so the auger flights are this helical thing that's wrapped around the center shaft, but the hollow stem is the center shaft itself. And in this case, this centerpiece here is a hollow tube. And during the drilling process, this piece right here is put inside the center hollow tube to form a single solid, or to form a single unit. And what happens though is that this tube can be opened up. You can pull this piece out, and you have then a tube that extends down to the bottom of the hole. So this tube, the hollow stem on the hollow stem auger, is what holds this hole open and allows you to access the full length of the hole during the drilling process. One reason why you might want to do this is in order to sample the materials at the bottom of the hole. And so here's another picture of a hollow stem auger, and we can see this center rod and this center piece down here that's plugging the hole during the drilling process. And then when you get to a certain depth, you can pull that out and put this thing in, and this is what's called a split spoon sampler, and it just consists of a tube that can be split in half, and this tube is pushed into the ground, and sediment goes up inside of the tube, and that sediment then remains in the tube. When you pull the thing out, you take this end cap off and unscrew it here, and this thing, there's an axial cut right like that. So this thing comes apart, and you can then get a sample of the material that's at the bottom of the hole. So the hollow stem auger allows you to sample during the drilling process, and that allows you to find out what's in the subsurface. And then also when you're done drilling, you have an open tube that goes down to the bottom of the hole, and this will allow you to put the casing in that will ultimately be your well. So here's a auger rig, and you can see the mast up here that is used to pull the augers up in the air while they're attached to the auger string that's going down into the ground. Here's a picture of a rather large hollow stem auger, and you can see that tube is maybe 10 inches in diameter, and the auger flights are really rather narrow compared to the diameter of the tube. One thing too that I should point out, that it should be fairly clear that this is good for soils and sediments and saprolites, material that can be cut using this shearing process. So that'll be a restriction. There's relatively shallow depth limitations. I say over here probably 30 to 50 meters depth would be about as deep as you would want to go. So I think that's most of what I want to say about this. One thing too that I should point out is that these two diagrams that I show here of the hollow stem auger have the auger and then this inner rod, and that's shown here, and that's this thing. What's done is that in some cases this inner rod is used, but it's fairly cumbersome to use because it involves each time you add an auger, this piece is usually 5 feet long, and so every 5 feet you have to add another piece of auger, and each time you do that you would need to add this rod, and so that just makes it a little bit extra cumbersome. And so what's done is to say, well, if I don't need to obtain samples during drilling, then I can just plug up temporarily the bottom of this open hole here. And so you have a thing that looks like a stopper, a wooden stopper, and that's just pushed here into the bottom of this tube, and you drill down to depth, and then you go inside with a rod and knock that out the bottom. And so that avoids using this thing, and it simplifies the drilling process. So it's great. You can do that if all you really want to do is create a well and you don't want to take samples as you drill. Okay, so this is the mud rotary and air hammer techniques. These are used for drilling holes into rock, into good, strong rock. If you tried to drill into rock with an auger that's using a piece of cutting steel or carbide, some kind of metal that is used to cut rock and shear, what happens is that the abrasiveness of that process will quickly wear out the metal. So you just simply can't cut rock in shear with this shearing type of motion. And so what's done instead is to create the cuttings to break the material in by crushing it. And that's done using a bit like this. This thing here is a tricone bit, and there are 3 cones on it. So there's one cone, there's one cone, and there's another cone over there. These cones rotate as this bit rotates. And the important thing is, or an important thing is, that you see these little buttons right here, these little protrusions. So those are either hardened steel or carbide, and as the bit rotates, these cones rotate, and as they rotate, these buttons progressively push down onto the bottom of the hole. So you can see that over here, I think. As this bit rotates, these guys are rotating, and as it's rotating, this, say that bit right there, that little piece of carbide, is, if this is rotating around like that, then this little piece of carbide is moving around and going to push down onto this bottom surface, just with a small degree of additional rotation. Okay, so when that happens, you have something like this. This is the bottom of the hole, and here's this carbide bit, and it rotates down and pushes down on the bottom of the hole. Well, it pushes down with quite a lot of force, and the rock right there is broken. It's crushed. And each time one of these carbide bits pushes down, it crushes a little bit of the rock, and that's how the hole is made. That's how the material is cut. It's cut by crushing. So this is a rotary bit. It's often used with mud, and the mud is injected down the drill string here. It comes out through ports in the side of the bit, and then as these buttons, these carbide buttons, crush the material at the bottom of the rock, or bottom of the hole, the mud that's circulated through removes the cuttings and transports them up to the surface. So in some cases, high velocity air is used to remove cuttings, and that's a technique called air rotary. So another technique that is related to this because it cuts rock by crushing it is with an air hammer. And here's a little sketch of an air hammer. And this thing has very high velocity air injected down into it. And what happens is it goes down and there's a weight in here, and the plumbing system within the air hammer causes this side to be pressurized and then this side to be pressurized, and that causes this weight to go up and down very rapidly. This is how a jackhammer works. So when the weight comes down, it hits it hits an anvil right here, and then causes the bit, which is right here, to be driven down onto the bottom of the hole. And there are little carbide buttons on the bottom of this bit that crush the rock at the bottom of the hole. And then the high velocity air that is used to cause this weight to reciprocate to work the hammer, then exhaust out the bottom of the hole. That picks up these particles and entrains them in this high flow of air and brings them out of the ground. So that's an air hammer, and that's the most common technique around here that's used to make holes in rock. All of the wells in the lower well field were used or were drilled that way. So here's a tricone bit. There's one of the cones right there, and you can see these carbide buttons quite well. There's another cone and there's another cone behind. And so this is for an air rotary rig, and the air comes out here and trains the particles and brings them back up. Here's an air hammer. This is viewed from the side. This is the bit itself. And if we look at the bottom of the bit, we can see again these carbide buttons right there. So the hammer is moving up and down with a lot of force. When it goes down, it slams down, and these carbide buttons are slammed into the bottom of the hole, crushing the rock right below them. And so this bit is rotated slowly so that these carbide buttons progressively are hammering on new material. And then the air comes out here and brings the cuttings up. So when you see this operation going on, you see a very high flow of air coming out, and it has these sand-sized particles that it's entraining. Often there's water that's coming out as well. Okay, so here's a diagram that shows the various different conditions for the air rotary, mud rotary, and air hammer. And it really depends on the kind of material that you're trying to drill through. So if you're drilling through hard material, igneous and metamorphic rock, that's really the domain of the air hammer. And that's what's shown there. If you're drilling through sedimentary rock, these guys here, limestone, sandstone, or shale, so it's rock, but it's a lot softer than igneous or metamorphic rock, and so that's really the domain of the air rotary. I guess I would also put in here saprolite. And then the unconsolidated material, this is mud rotary. Okay, so those are the main methods for drilling wells. There's another technique, though, that's very important. It's not so much important for drilling wells that are used to remove fluids, though, because it can create wells, but it creates very small diameter wells, ones that are really much more suited for monitoring. This is a technique called direct push, and It differs from what we've seen with the previous techniques in that it doesn't really remove any of the cuttings. So it's creating a hole, but instead of taking the material that was where the hole is now, instead of taking that material and removing it from the ground, it simply pushes it aside. So it can really only work in material that's relatively soft and can be pushed aside. You could never do this in rock, for example. But if you take a tube, or if you would take a rod that's, say, 1.5 inches in diameter and has a point on it, and you push it down in the ground, it's going to go if the material is fairly soft. You can push it in the ground, and then if you start hammering on it, you can get it to go even further. And so that's basically what's happening here. This is a geoprobe or a direct push rig, and this is a hydraulic hammer. So it's essentially a jackhammer, and this is a steel tube. So this thing pushes down and hammers and drives this tube in the ground. Well, what can be done then is the tube is hollow, and there are various different configurations that have an inner rod, much like what we saw for the hollow stem auger, but in this case we have an outer tube and an inner rod that has a point on it. You push this thing in the ground, you hammer it, and then you can pull the inner rod out and go and get a sample from the bottom of the hole. You could, say, pull the inner rod out and drive it down and get a soil sample, or you could get a sample of water sample. And so these direct push techniques are used in the environmental industry extensively because it's a way of getting samples of the potentially contaminated sediments or water, and it's relatively quick and relatively inexpensive. So if you have a contaminated site, you really want to understand the distribution of the contaminants, and that means making lots of samples. And so you got to keep the cost down. And these direct push rigs, often they're called geoprobe rigs, and that's because you can see here, there's Geoprobe. Geoprobe is a manufacturer of these rigs. They were really one of the first, perhaps the first, to make this style of rig, although there are a variety of other manufacturers these days. And so geoprobes or direct push rigs are widespread in the environmental industry. And if you go into the environmental industry, you will almost certainly run into these probably on your first day on the job because they're very common. Okay, so here are some looks at some of these different rigs. This is what an air rotary drilling rig looks like. This thing right here is a big air compressor. See, it's a pretty good sized truck. And then down here on the bottom we see some looks at geoprobe rigs. This is one that's mounted on a track for getting around a site. It has to be put on a trailer to move it from one location to another. Here's a geoprobe set up. This is during field camp, and this is one of the field campers using it. It's another look at a small geoprobe rig. We have a geoprobe rig in the department that mounts on the back of a pickup truck. This is a hollow stem auger rig. You can see the hollow stem auger right there. Generally, these rigs, the hollow stem auger rigs, are smaller than the air rotary rigs, but bigger than the geoprobe rigs.